Welcome to the second video in SLO10, where we'll be looking at another kind of reagent that we call cuprates, or organocuprates. These were developed in the early 1950s at UC Berkeley, go Bears, by a chemist with the last name Gilman. And so these are also sometimes called Gilman reagents, depending on who you're talking to. So what Gilman and others had realized for some time was that Grignard reagents tend to be only somewhat selective when they react with alpha-beta unsaturated carbonyls, but that they typically prefer 1,2 addition. So our problem was Grignard and organolithium nucleophiles prefer 1,2 addition. So how could we do a selective 1,4 addition to make a new carbon-carbon bond? And so Gilman, along with coworkers at Berkeley, started to try different kinds of metals. They kind of had this idea that if they changed the nature of the metal from magnesium to something else, that might change the reactivity. And we've seen that before in this class, right? So it's not necessarily a crazy idea. And eventually what they found was that they could use copper instead of magnesium, but there's special kinds of copper reagents. So these Gilman reagents, or these cuprates, have unusual structures. So I'll draw an example of a cuprate here. So an ethyl group. So I've got a carbon-copper bond, and then another carbon-copper bond. And if this copper is at the +1 oxidation level, which is what they are in cuprates, and we treat these carbon groups as anions, which is also appropriate given what we know about electronegativity, then this copper is negatively charged. We've seen these kinds of effects before, where if we take a metal or something like that, maybe an aluminum, for instance, or a boron, and we add groups to it like hydrogens or ethyl groups, for instance, it's actually the things attached to that metal or in the case of aluminum or boron, like non-metal center, that actually becomes nucleophilic and basic, and that's true for cuprates also. So these carbons that are directly attached to the metals, these are nucleophilic sites. And it also means that we need some kind of a cation that goes along with this. So I'm just going to write M plus for now, a generic metal center. Could be a sodium or a lithium, for instance, lithium plus, sodium plus, we'll see. There are other kinds of species that look a lot like this also, but they're not cuprates. So this ATE tells us that there's a negative charge in a polyatomic anion, which is definitely true. There's also organocopper species. So a corresponding organocopper would be still copper at the +1 oxidation level, but it would be like that. So just one ethyl group, one copper atom, no negative charge, no cation. So this would be called like ethyl copper 1, right, to give us the oxidation state information, right? So remember you learned in Gen Chem like iron 3 chloride or something like that. This would be like ethyl copper 1. So we've got two different kinds of species. Just to make sure you remember how to assess reactivity in these cases, I want you to compare the nucleophilicity of this carbon to the nucleophilicity of the carbon attached to the copper in the organocopper case. So which of these two organometallic reagents is more nucleophilic? So I got a chance to think this over. And if we actually analyze the structures, we can realize that there's less of an electron buildup on this carbon than there are on these carbons because of the nature of the metal. If this copper atom is essentially overloaded with electron density, it's going to push some of that electron density back onto the things to which it's attached. This copper isn't overloaded, so it's not necessarily donating much electron density to the carbon center, and therefore we could say these cuprate structures are quite a bit more nucleophilic than organocopper species. So we can say these are much more nucleophilic. If you like, you could think about the copper as an inductive donor, a very powerful one. So how do you make cuprates? How did Gilman make cuprates? They look like unusual structures. So it turns out it's not that bad. If you were doing this research, you would probably think, well, I want to try to make these in the simplest way that I can. Like, what if I could just like trade one metal for another in an organometallic reagent I know how to make? So maybe I'll use like a Grignard reagent, for instance. So we could start with an ethyl group attached to a magnesium. And that magnesium is going to have some halogen on it. I'm going to choose bromide because why not? It could be chlorine or iodine. And all I'm going to do is react this with a source of copper 1. Right? So I need to choose the oxidation state of copper. That turns out to be really important. And it turns out that copper iodide, or Cui, is really good for this. It's one of the only really highly stabilized and somewhat soluble in organic solvents copper 1 species, so we use this. This is at the +1 oxidation state. That's critical. And so we're just going to trade the copper for the magnesium. So we make a new carbon copper bond, and we actually end up making 2 of those. So we have 2 equivalents of our ethyl magnesium bromide, 1 equivalent of the copper iodide. We end up with both of those groups attached to the copper. The copper is negatively charged. The cation here will be a magnesium and still a bromide unit bonded together. So I'll have like an MgBr cation. So the magnesium is a +2 oxidation state. And then if you actually carefully follow this, I'm going to have another atom of magnesium, another atom of bromine, and I'm going to have that iodide anion. So the other species I'll have here is MgBrI. So a magnesium ion or cation with 1 Br minus and 1 I minus. Okay, so we could write this in a variety of ways. We could write the structure out just like this. We could also abbreviate it. So this could be 2 ethyl groups, so ET2, and then those are attached to a copper, so we'll write Cu, and then we also want to indicate the kind of cation present, so we'll write MgBr. So ET2Cu MgBr. I'm not even going to try to pronounce that phonetically because I'll die. And so you can use these kinds of like shortcuts, for instance, or the full structures to denote what's going on with a cuprate. You can do the same kind of chemistry with other types of Grignards or organolithium species. So let's look at an example where we actually make a cuprate from an organolithium. So we'll use good old Feely, and we'll treat this with still copper iodide. That part's no different. We also know that we're going to need to have 2 copies of this, right? The first copy makes phenyl copper, right? Just like the first copy here would have made ethyl copper. And then that second equivalent of the Grignard makes the cuprate, right? And then here the second equivalent of the organolithium will make the cuprate. So we're going to have 2 benzene rings attached to copper. It's like a really fancy Mickey Mouse, one that maybe got stolen from a plumbing unit inside of a house or something. Minus, now I'll have a lithium cation instead, and we'll also make lithium iodide. Okay, so to abbreviate a structure like this, we could draw it, that's fine, it doesn't take that long. Or we could write phenyl, right, the benzene rings and substituents, 2, Cu-Li. That works too. So either of those ways of denoting things. So general strategy, right? 2 equivalents of whatever organometallic nucleophile you like, organolithiums, Grignards, plus copper iodide is going to give you the cuprates that you need. There are even more sophisticated ways to do this that we won't touch on. So let's see how these cuprates actually behave when we put them back into reactions involving these alpha, beta, unsaturated carbonyls. So what I'm showing you is the same reaction that I showed you to open up this SLO video series, but I've made one change. I'm using a different nucleophile. So rather than using ethyl magnesium-bromide, we're using our diethyl cuprate reagent instead. So in principle, we make the same products. We have the 1,2 addition product, and we also have the 1,4 addition product. But when we do this reaction with cuprates, we get less than 10% of our 1,2 addition product and more than 90% of of our 1,4 addition product. So one of the big takeaways here is that these cuprates are highly selective for 1,4 addition. In a lot of cases, you don't even see the 1,2 addition product at all. So these are actually pretty beautiful reagents. Gilman really kind of stumbled into something awesome here. This is so true, but I would recommend that if you see copper, that's a good visual indicator that you're doing a conjugate or a 1,4 addition. Kind of just a good mnemonic to have for yourself here. I wish I could tell you why this is true. We know it's true, experimentally it's true. I've run a number of these 1,4 additions using cuprates in my career, but we still don't have a very good mechanistic picture about what's going on here. There are different proposals. Some of them involve radicals. Some of them involve redox cycles of the copper. So the copper starts out at the +1 oxidation state and then ends up in the +3 and then gets reduced again. But a bunch of different hypotheses. It's also possible that the mechanism of these reactions or where their selectivity comes from depends on the structures of the electrophiles. Like the reasons could potentially change. So this is one of those maybe a little dissatisfying areas where it's a reaction we know works well. It's worth having in your tool belt, especially for synthetic problems, but we don't have a great idea about why it's happening. So let's look at a couple of other examples where we use cuprates to do these 1,4 additions for alpha, beta, unsaturated carbonyls. So it doesn't have to be a structure like this. We could choose other things also. So you could imagine doing this with like a cyclic, what we call enone. So this is like an alpha, beta, unsaturated ketone. And so let's change up our cuprate a little bit just so we get some variety here. So these structures can actually be fairly complex. So we could have this kind of a structure here. Let's say we made it from some kind of organolithium species, so there'll be a lithium cation floating around. And we do need a water workup. We'll talk about that in just a minute. So I need to decide a couple of things, like usual. I need to decide electrophilic sites. I've got two possible ones, either the carbonyl carbon or the beta carbon because of this conjugation. But I see copper, right? And so I'm going to remove my 1,2 possibility. And now I need to decide which atom within my cuprate is actually nucleophilic. And so just like it's been true for all of my other organometallic species or nucleophiles, it's going to be the atom that's bonded to the metal. So this is a symmetrical cuprate. I'm going to choose one of the two carbons that's directly bonded to the copper, and I can make that choice arbitrarily because they're the same as each other. So I'll choose this one as my nucleophilic site, and I'm just going to connect these two species. So the thing that's different about cuprates is, remember, they actually go through this intermediate that's an enolate. So I'm going to draw the structure that forms after just the first step. So the cuprate's been involved, but no water yet. So I know that I'll make an enolate, like we said. I also know that I'll make a new CC bond between my electrophilic beta carbon and my nucleophilic carbon bonded to the cuprate, or the copper center. So you'll notice the stereochemistry is conserved, right? There was a trans relationship between the copper and the methyl, and there'll be a trans relationship between the methyl and the new CC bond in this case. And then we also need to think about the fate of the copper species. So the electrons in this carbon-copper bond, at least formally, we don't know like mechanistically how exactly this works, but this is a reasonable model, would be to say that these electrons get donated into the new CC bond, and then we have a rearrangement of electrons within the alpha-beta conjugate, alpha-beta unsaturated system. So that means that this copper is still copper 1. Its oxidation state's not changing, and that means that we're actually going to make an organocopper. So the other species here will be Cu with a alkene attached, and that's it. Right? The lithium will be associated with the enolate. It's just like negative charge, I like negative charge, ooh. And so it's just going for the ride, and this is what's present before the quench. So when we put water into this mixture, a couple of things happen. And the most important is that we can protonate the enolate. So the quench protonates the enolate. And that protonation will give rise to a new CH bond. So I'll actually draw my water molecule out. I should have done that. That was a mistake. All right. So that will give me a I'll lose my colors. Product that looks like this. There's the new CC bond. It's just a spectator for the workup, and then there's my new CH bond there. So the workup is important. We can't skip that. Otherwise, we just have an enolate that's staring back at us, and that enolate could do other things, for instance. So the organocopper, I told you these weren't very nucleophilic. And if they're not very nucleophilic, you probably know what else is true about them. They're not very basic. So a lot of times these species will survive for a little period of time with the water present, right? That's how unreactive some of these compounds are. Okay, so we've looked at a couple of examples of what we'll call, you call them 1,4 additions, conjugate additions. Some people just kind of combine everything and say, oh, well, I'm doing cuprate additions. But the idea here is that there's something about the copper that directs our nucleophilic carbon to the beta carbon of our alpha-beta unsaturated system. So we'll look at one other example here. We won't go through all the mechanistic detail, but it's good to just have a few different kinds of examples that you've seen. You're not restricted to alpha-beta unsaturated ketones and aldehydes. This works with like alpha-beta unsaturated esters and amides as well. So look at an ester case. So we'll look at this species, and we'll do Me2CuMgCl and a water workup. So here I'm going to play the same game. I know I've got 2 electrophilic sites. Boom. And the beta carbon, boom. And I know that I've got a copper. So I know that I'm dealing with a 1,4 addition. And then the last thing for me to do is decide, well, what am I transferring? So one of the downsides of the nomenclature where we kind of condense these names down is you have to envision what Me2Cu means. And that means that there's one methyl group on each side of the copper atom, essentially. So there's like one carbon-copper bond for each methyl. And that means that one of my methyls will be nucleophilic. That's a C. Okay, and so I also know there's a workup in there. So I'm going to try to do all this in one go. I know part of the structure is not going to change, so my benzene ring is still there. But I know my alkene is going away. I'm going to be consuming it as part of this 1,4 addition. So at the beta carbon, I'm going to add my methyl, so my new CC bond is here. And there's a couple ways you could do this. You could draw the enolate and then protonate the enolate, or you could imagine, well, okay, if I'm breaking the CC pi bond here, I need to put things where it was. So I'm going to add the nucleophile to this side, and I'm going to add the proton to this side. So it looks a little bit like a net addition to this to the pi bond. There's my new proton from the workup. And the ester seems to have been unchanged. Right, so our mnemonic here is nucleophile and proton to alpha carbon. Okay, so you can imagine lots of examples like this. There's a ton of practice problems in the SLO document where you can work with adding cuprates to different kinds of electrophiles, for instance, so I won't belabor the point anymore. I just want to show you one other aspect of this 1,4 addition with respect to another kind of a nucleophile in the next section of the video. In the last section of this video, we'll be looking at another kind of a reaction that's called a Michael addition. So this name gets thrown around a lot, sometimes inappropriately. Technically what it means is 1,4 additions involving carbon nucleophiles. So that technically would include cuprates, I tend to call those Gilman reactions or cuprate additions. Michael additions, to me, I'll think about enolates, and especially enolates that are relatively stabilized. And so one example of a Michael addition is what we see here. So we have our alpha-beta unsaturated carbonyl. In this case, it's an enal. And we have this beta diketone. And in the course of reacting with methanol as a solvent and some sodium methoxide, so there's an O- here, we get this product. So the first thing that I'll notice here is that there's a new CC bond between the position here, between the carbonyls, and the beta carbon of my enal. So that means that my beta carbon is probably electrophilic, as we've been talking about in this SLO, and that means that this carbon here must have been nucleophilic. But right now it's not. So I need to think about how that would have been possible, and that probably means that the other reagents will be involved in making this carbon nucleophilic. So I want you to pause your video and propose how you can end up with a nucleophilic carbon here using these reagents. So you have a proposal for how this carbon here becomes nucleophilic, and it must involve these compounds. You probably noticed that this oxygen of the methoxide is basic. It's the conjugate base of an alcohol. And so what we might propose, if we start to think through a mechanism, that's not how you spell it. Yes, first spelling mistake. For this Michael addition is that we actually make an enolate in our first step. So this proton is very acidic. We talked about this a little bit in the last SLO. So its pKa is around 10. And the product that we're going to make here, methanol, has a pKa that's higher than that, about 15. So unlike the enolates that we really spent a lot of time talking about last SLO, this is actually a favorable deprotonation because of the unusual acidity of the proton between two carbonyls, right? So it's not like the base always gives you reversible or irreversible enolate formation. You do have to take into account the acidity of the species you're starting with. All right, so that double bond sucks, so I'm going to clean it up. So here's our enolate. And now we can think about the enolate, which is nucleophilic at this carbon, which is what we were trying to explain. It could react with the beta carbon of my enal in a conjugate addition or a 1,4 addition. So the way that would look from this resonance structure of our enolate would be like that. And if I follow my arrows, I'm going to make my new CC bond for sure, but I won't make this product entirely, not exactly. I'm going to end up with an enolate. So I went from one enolate to another enolate. Remember, anytime you're doing a conjugate addition or a 1,4 addition or a Michael addition, they all kind of mean the same thing. Anytime you add any nucleophile to the beta carbon, you make an enolate. So here is what we actually make, and now we need to have how to figure out how to get from here to the final product. So if I look at the difference in structure between this compound that I just made and what I know I eventually isolate from the experiment, I definitely don't have an enolate. And if I look carefully, I have two hydrogens on the carbon alpha to my aldehyde, whereas here I've only got one. So I'm looking for a source of protons, which, oh hey, perfect solvent, nice. So we can use the methanol, which was a solvent here, to also protonate the enolate here that we made as a consequence of our 1,4 addition. So that's going to give rise to the product that we isolate. Not a double bond. I'll draw in those hydrogens explicitly just so we can keep track of them. And the conjugate base of methanol. So one of the things that we notice here is that this is actually catalytic in methoxide. So this is an example of a base making a better nucleophile as a form of base catalysis. Okay, so Michael additions typically work this way. They typically, but don't have to, use these stabilized enolates. So Michael additions, second spelling mistake, often use stabilized enolates. So these would be enolates from like beta keto esters, beta diketones, like 2 carbonyls flanking a single carbon unit with a proton. That's where these stabilized enolates are going to come from. You don't need that. You can do normal enolates and get reasonable amounts of 1,4 addition, but the reactions aren't as selective. So these stabilized enolates, they tend to be the most selective for 1,4 addition over 1,2. Nope, 1,4 addition. Which brings me to essentially the final point I want to make in this video, and that's how do you know if it's a nucleophile maybe we haven't talked about, or maybe no one's thought about it before. Like, how could you predict whether you're going to do mostly a 1,2 addition or a 1,4 addition? There aren't any hard and fast rules here, and there's really not a lot of agreement in the organic chemistry community about like what the rules should look like. In my observation from looking at reactions and performing them over the last, well, I'm not going to tell you how long because it'll feel even older than I already do, I actually use pKas as a guide, right? So if I think about the nucleophile and its conjugate acid, so like a pKca, if that number is like less than 30, I'm probably going to be doing mostly 1,4 addition. Like, it's reasonable to assume that conjugate addition will be the major product. And the reaction will typically get more selective for 1,4 addition as the nucleophile becomes more stable, right? So remember, as our pKca becomes a smaller number, right, the nucleophile is less reactive, right? That's kind of like what we saw here. Highly acidic proton, this is the conjugate acid of the nucleophile we used, right? And so that also correlates with high selectivity. So most enolates come from ketones or esters, pKas of 20 or 25. And in those cases, we would expect to see 1,4 addition. On the other hand, Grignards come from like alkyl groups or alkanes, and so those pKas are like 50. And in those cases, we typically see 1,2 addition. There's one notable exception here, and that's cuprates, right? So copper is doing something which we don't really understand, that's overriding this kind of correlation between the acidity of where our nucleophile came from and what that nucleophile's preference is for 1,2 versus 1,4 addition. So another use of pKas is, predicting whether or not you do 1,2 or 1,4 addition. So in the next video, we'll be looking at essentially putting together a lot of what we've done in SLO10 and 9 into a really beautiful reaction that we'll probably spend an entire video going through a single example of.